we have SDR based low latency communication system. So first question arises, why do we have that solution? So if we talk about mission critical applications such as industrial closed loop communication system, telesurgery, autonomous driving, all these system needs highly reliable and low latency data. So another motivation comes from 5G. 5G also have a category that is called URLLC, ultra reliable low latency communication. So these things motivate us to have a solution that must have low latency. So we have a solution, low latency flexible solution, and this is a very basic architecture of our solution. We have used 802.15.4 standard to implement our concept. In fact, our solution is based on PHY and MAC layer. The PHY layer is implemented on FPGA and the MAC layer is implemented on processor. So and both of them are implemented on Zinc 7000 architecture. So how do we achieve low latency? That is really a good question. So, so we have done many improvements from MAC layer to our front end. So for example, we have used pipelining architecture here in FPGA that helps to achieve low latency. Another modification that we have done in the MAC layer in the processor. So normally a processor need to read and write data from memory. We have a DDR-RAM memory. So DDR-RAM memory has, normally it's a large memory, so it has high access time. So it also contributes to the latency. So we replace that DDR-RAM with OCM, on-chip memory. So in that way, so you don't need to cache the data. You can directly access the data without caching. So it also helps to improve the latency. The third main thing that we have done in improving the latency is our front end. So our system is operating in time division duplex mode. So it means you have to switch from RX to TX, TX to RX. So while switching, you have to spend some time, and that time is also very critical in time critical application. So according to our measurements for that, our front end, the switching time, TT, turnaround time, so-called TT, so that has a value around 20 microseconds. So that 20 microseconds is again a very huge amount of time. So we done some improvement here, and we have turnaround our switching time around 0. So all this modification helps us to achieve very low latency communication link. So next thing is, okay, we have very low latency solution, but it's really highly configurable because it's SDR based. So this is our solution results, and this is a commercial chip. This commercial chip is also 82.15.4 standard base. So in order to have a fair comparison, we have compared our results with the standard chip. So our solution is backward compatible. So it can operate in a standard mode as well as it can operate in some advanced mode. So in a standard mode, we have compared our results with a commercial chip. So this is a round trip time. It means if you send a packet and receive back, and that time is called round trip time. So we have sent 28 bytes and compare the results. In a standard mode, we have 2.05 millisecond. In case of commercial chip, we have 2.44 millisecond. Even in the standard mode, we have a better latency performance, and this is about 16%. And how do we achieve? I already explained the steps to achieve a better latency. Another thing, we also have advanced mode, so-called advanced mode. In advanced mode, we can achieve even better latency. We can see that here we have 2 milliseconds, we have 1.09 millisecond, almost 2 times lower latency. And how do we achieve that? And this latency change is over the air. I mean, you can change in runtime according to your application. So we call that concept tunable latency. So we had a concept of tunable latency and ultra low latency. So that concept is implemented on that standard, but it doesn't mean that this concept is only for that standard. It can be implemented on any standard. So this is our concept only. Yeah. Now I'm talking about low latency So we also have a live demo for that application. So I will just explain how the demo is working here. So we have a balancing robot here. So that how this demo works, I will give a very short description of that demo. So what happens at the very beginning, the robot sends sensory data to SDR. That SDR means it has that architecture. It takes the data and send over the air to another SDR. We call it a cloud, and we simulate it like a cloud. And based on the sensory data, it will issue balancing commands, and these balancing commands come back over the air to the SDR, that SDR, and that SDR, upon receiving the data, receiving the balancing commands, it will give back this balancing command to the robots. And based on the received data, a robot will try to keep itself balanced. You know, that round trip time is very critical. So here it is sending and receiving back. If it is able to receive the data within a time limit, and that is defined by balancing algorithm, the robot will remain balanced. Otherwise, it will lose its balance and it will fall on the ground. So now I will show the demo here. You can see that robot is almost balanced here. So the robot is working on a TDMA scheme in a MAC layer. So in TDMA we have beacon slots, we have TX slots, we have RX slots, and we have no operational slots. So we have a customized super frame here. So as I mentioned that so the basic flow is like that. So we are sending a sensory data, and sensory data will go to this node, and that node send the data over the air to that node, and it will send back that data to the node 1, and this data is called balancing commands, and it will come back via UART to my robot, and based on the balancing command, my robot will try to keep itself balanced. So you know that as I mentioned, the time from this node to that node and back is really critical for that balancing algorithm. So that duration is 2 milliseconds in this application. I mean, the TX slots in a TDMA scheme or RX slot is 2 milliseconds. So next thing I mentioned in my presentation, that we have a tunable latency. So that tunable latency is just exposed parameters that is given to the upper layers. So I can change the latency over the air here. So you can see that if I increase the latency, the system start to become unbalanced. So I will change the latency now. You will see here, you know, the system start to become unbalanced.